Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Please allow me to reintroduce myself. I'm Philip Emeagwali. I began supercomputing at age 19 on June 20, 1974 in Corvallis, Oregon, USA. Back then, there was no computer in my country of birth, Nigeria. In 1974, the parallel supercomputer, that's the precursor of the world's fastest computer, was mocked and dismissed as science fiction. Parallel processing was an unproven technology that couldn't be harnessed to achieve the world's fastest computer speeds of a vector supercomputer. The unproven technology couldn't be used to solve the most compute-intensive problems, such as executing computational fluid dynamics codes, including executing high-resolution global climate models, and doing so to foresee otherwise unforeseeable long-term global warming. In the 1980s and earlier, everybody ridiculed parallel supercomputing. The technology was mocked and dismissed as unproven and as a tremendous waste of everybody's time. My contributions to the development of the computer were these. I was in the news for becoming the first person to use the slowest processors in the world to discover the fastest computing in the world and solve the most compute-intensive problems in the world. My scientific discovery, called fastest computing, occurred at 15 minutes after 8 o'clock in the morning of July 4, 1989, in Los Alamos, New Mexico, USA. Briefly, I discovered how to execute the world's fastest computing with the world's slowest processors. My discovery of the fastest computing revolutionized the essence of both the computer and the supercomputer. The world's most powerful supercomputer cost $1,250 million, and it costs 40% more than the mile-long Second Niger Bridge at Onitsha, my ancestral hometown in Nigeria. The supercomputer is used to solve the most compute-intensive problems in mathematics, science, and engineering. Without supercomputing across millions of identical processors, these grand challenge problems will be impossible to solve. A new technology for fastest computing creates new sciences. The world's fastest computer opened the door to unexplored areas of mathematics, physics, and computer science. The diverse applications of the supercomputer range from oil exploration to a surer prediction of global warming. The earliest experiment across a massive ensemble of processors in which a grand challenge problem was solved occurred at 15 minutes after 8 o'clock in the morning of the 4th of July, 1989, in Los Alamos, New Mexico, USA. That first experiment led to my signature invention, which is the new knowledge that powers the world's fastest computer and enables it to solve problems that were once impossible to solve, and solve them in parallel and across my global network of processors that outline and define my new internet. Shortly after my experiment of July 4, 1989, I was in major US newspapers for winning the highest award in supercomputing. That first experiment provided the blueprint on how to parallel process and do so across a new internet. That never before visualized internet was a vast ensemble of 65,536 off-the-shelf processors that tightly encircled a globe. Those processors were coupled and shared nothing. My 2 raised to power 16 identical processors communicated synchronously and computed simultaneously, and did both to solve the most compute-intensive problems in the scientific and engineering worlds. In an email, a 12-year-old writing the biographies of famous computer pioneers asked me, "How are supercomputers used in Kuwait?" The supercomputer market is valued at $45 billion a year. The energy and geoscience industries buy 1 in 10 supercomputers. The Bogan oil field in the desert of southeast Kuwait was discovered in 1937. The Bogan oil field contains up to 72 billion barrels of recoverable crude oil reserves. The Greater Bogan oil field is the world's largest sandstone oil field. The Bogan oil field is declining at 14% per year. Fastest computing, executed across billions of processors, is used to recover about half of the crude oil reserves inside the Bogan oil field. In 1989, I was in the news for discovering how the slowest processors in the world could be harnessed as the world's fastest computer and used to discover and recover otherwise elusive crude oil and natural gas. The parallel supercomputer became known to a broader audience after my scientific discovery of the 4th of July 1989. That discovery yielded the world's fastest computer speeds that I recorded across the world's slowest processors, and recorded while solving one of the world's most compute-intensive problems. I arrived at that frontier of knowledge by contributing to the knowledge discovered by research scientists whose names were lost in the midst of time. In the past 100 years, the population of the scientific community has grown by 1,000-fold. A century ago, there were only 1,000 physicists in the world. Today, we have 1 million physicists in the world. We could say the same of mathematicians. The body of knowledge, now described as information and communication technologies, has grown exponentially since the 1940s. The parallel processing problem, which I solved in 1989, was then classified by the US government as the grand challenge problem of supercomputing. My solution of that compute-intensive problem traversed extreme-scale partial difference equations of computational linear algebra, traversed partial differential equations of calculus, traversed large-scale computational physics, and traversed the supercomputing across up to 1 billion processors that made the news headlines because I parallel processed to solve the most difficult problem in mathematical physics. I solved that problem across a new global network of off-the-shelf processors that outline and define a never-before-recognized internet. That grand challenge problem was far more complex and compute-intensive than the calculus problem that Isaac Newton solved 3 centuries and 3 decades ago. It's more difficult to invent new calculus than to understand the calculus in textbooks. For that reason, contributions of new partial differential equations to the existing body of mathematical knowledge is more valuable than the mastery of mathematical methods. Nonetheless, the mastery of mathematics and physics is always a precondition for the invention of new partial differential equations as well as the world's fastest computers for solving them. As a computational mathematician, I invented discrete approximations that honor both the governing partial differential equations of calculus and their underlying physics. My contribution of the world's fastest computing to mathematics and physics is used to extract crude oil and natural gas that are buried up to 7.7 miles deep and formed up to 541 million years ago. An oil field is about the size of Abuja, the capital of Nigeria. An oil field is a mixture of different materials which has properties that vary from point to point. Often the properties may not have the same value along perpendicularly different directions. The value along the z direction might be different when compared to those along the x and y directions. Such differences, called heterogeneities and anisotrophies, make my supercomputer model more complex. As an aside, Isaac Newton wasn't a scientist. The term scientist was coined about a century and a half after Isaac Newton died. Instead, Isaac Newton described himself as a natural philosopher, not as a mathematician or a physicist. Contrary to what is widely believed, Isaac Newton devoted most of his careers to researching occultism, not to searching for new laws of physics. Looking back retrospectively, there are 1,000 times more geniuses today than a century ago. Yet in the 1940s, the likes of the physicist Albert Einstein couldn't parallel process, in part because the technology and the technique were then unknown. For those reasons, they couldn't accurately solve an initial boundary value problem of mathematical physics, such as global climate modeling to foresee long-term global warming. Global climate modeling is the most important problem in computational physics. If I can travel back in time to 3 centuries and 3 decades ago to Cambridge, England, I will explain to Isaac Newton how we use the system of partial differential equations of calculus that encodes the second law of motion of physics and use them to model the transport of pollutants through a groundwater aquifer. Solving this difficult problem of mathematical physics demands the simulations of a complex set of biogeochemical reactions that in turn is coupled with the simulations of the multi-phase flows of air and water. I will explain to Isaac Newton how the compute intensiveness of modeling groundwater aquifers and production oil fields increases when their solutions are governed by partial differential equations. Such equations account for multi-phase fluid flows and give rise to mathematical objects called tensors that represent heterogeneous aquifers that are characterized by anisotropic peak hydraulic conductivities. I will explain to Isaac Newton that a tensor is similar to a vector, but a tensor is more general than a vector. The array of components of a tensor are functions of its spatial coordinates. Finally, I will explain to Isaac Newton how and why many mathematical models are multi-physics and multi-scaled. The reason is that some phenomena are governed by different laws of physics and chemistry and occur over wide-ranging temporal and spatial scales. The science of today was the science fiction of Isaac Newton. Back in 1989, I was in the news because I was the first person to understand how to solve the most compute-intensive problems in supercomputing. I discovered how to tackle the world's most compute-intensive problems in algebra, calculus, and physics. I discovered how to solve them across a new internet. That's a new global network of 65,536 off-the-shelf processors and standard parts. That contribution to mathematics was the reason I was the cover story of the top publication in the world of mathematicians, namely the May 1990 issue of the Siam News. I was the cover story because the foremost mathematicians in the world were being informed that I discovered how to solve initial boundary value problems governed by partial differential equations that encoded the laws of physics. I discovered how to solve the most compute-intensive problems and how to solve them not merely on the blackboard or even on the motherboard, but across an ensemble of up to 1 billion processors that equidistantly surrounded the globe, and did so in the manner the internet circumscribes the earth. My discovery made the news headlines because in the 1980s, nobody else could execute the most compute-intensive global climate models and compute with the slowest processors in the world, and do so while recording the fastest speeds in supercomputing. The global climate model must be parallel processed to enable the climatologist to foresee otherwise unforeseeable long-term global warming. In 1989, I was in the news because I discovered the fastest computer speeds that are possible and discovered how to compute across a new ensemble of up to 1 billion processors that surrounded a globe, and did so just as the internet encircled the earth. I began supercomputing on June 20, 1974 at age 19 at 1800 Southwest Campus Way, Corvallis, Oregon, USA. On my 16th anniversary of supercomputing, I was credited in the June 20, 1990 issue of the Wall Street Journal for discovering how to compute together and how to communicate at once and how to do both across a new ensemble of 65,536 processors, and how to compute at the fastest recorded speed, and do so to tackle the most compute-intensive problems. Such difficult problems could only be solved by dividing them into billions of lesser compute-intensive problems that in turn could be solved only by a one problem to a one processor mapping onto a network of millions of processors. This problem to processor mapping is the substance of how the first supercomputer that computes fastest across the slowest processors is used to tackle the biggest and the most intractable problems in the mathematical sciences. As a research supercomputer scientist who came of age in the 1980s and in the USA, my goal was to contribute new knowledge, namely the speed and speed up across up to 1 billion processors. My record speed in supercomputing of July 4, 1989 was new knowledge that was used to actualize the world's fastest computing across over 10 million processors. My discovery was a milestone in computer history. My invention turned parallel computing from fiction to fact. In the 1970s and 80s, the world's fastest computing across up to 1 billion processors and its use to get more accurate solutions of initial boundary value problems governed by partial differential equations of calculus and physics was classified as a grand challenge problem. It was so called for a compelling reason. In the 1980s, attempting to harness an ensemble of 64 binary thousand processors and use them to emulate a virtual supercomputer was as difficult as attempting to make science fiction become reality. That grand challenge was the reason the farthest frontier of the massively parallel supercomputer had only one permanent resident. I was that permanent resident of the then unknown world of the world's fastest computing across up to 1 billion processors. In 1989 and in the USA, I was in the news because I witnessed the first dramatic upgrade in our understanding of the computer of tomorrow, not as a new computer per se, but as a new internet de facto. The computer will become the internet and vice versa. It's impossible to say exactly how the world's fastest computers are used. Some supercomputers, such as those used to simulate the shock waves emanating from the explosions of nuclear bombs, only exist off the record. The supercomputers for nuclear labs are manufactured without serial numbers, and oil companies protect their supercomputer simulations as trade secrets. I was coerced to sign non-disclosure agreements that prevented me from telling you everything that I know about the world's fastest computing. In the 1980s, the massively parallel supercomputer was only available to a few dozen scientists that worked within the US Federal Nuclear Research Laboratories. Today, such supercomputers are available to everyone. I was the only full-time programmer of the 1980s of the most massively parallel supercomputers ever built. That was how and why I became known as a supercomputer scientist. In an email, a 12-year-old writing the biographies of famous mathematicians and their contributions to the development of the first supercomputer that computes the fastest across the slowest processors, asked me, how do you become a supercomputer genius? You become a supercomputer genius by first deeply understanding the difficult mathematical problems that you must solve, and by deeply understanding how you must divide the most compute-intensive problems into up to 1 billion lesser challenging problems, and knowing how to solve them with a unique one processor to one problem mapping that preserves nearest neighbor nearness, and understanding how to solve such problems across the up to 1 billion processors that outline and define the massively parallel supercomputer. That supercomputer genius must be a polymath or a jack of several sciences. That supercomputer genius must be at home at the frontiers of knowledge in mathematics, physics, and computer science. The supercomputer genius must understand his computing machinery and know it forward and backward and even sideways. The supercomputer genius must be the first person to understand how to compute at speeds that were considered impossible, and compute to address some of the world's biggest challenges, and compute in a breakthrough way that's ranked as a milestone and that changed the way we think about the modern computer and the fastest supercomputer. It took me 16 years on the world's fastest computers to discover that I could compute at the world's fastest speeds and do so across the world's slowest processors, and do so to solve the most compute-intensive problems in science, engineering, and medicine. The world's fastest computing that's executed across 1 million coupled processors is the central knowledge that must be used to foresee the otherwise unforeseeable spread of contagious viruses that occurs during a once-in-a-century global pandemic such as COVID-19. My contributions to the development of the first supercomputer, as it's known today, made the news headlines because I discovered that parallel processing will become the vital technology that will be used to manufacture the world's fastest computers. I didn't merely discover the world's fastest computing across one binary million email wires, nor did I invent the technology by luck or serendipity. I discovered the world's fastest computing because I deeply understood the underlying mathematical physics that defined the compute-intensive problem that must be parallel processed across up to 1 billion processors. In 1989, and in the USA, I was in the news because I discovered how to solve the most compute-intensive problems in mathematics and physics, and how to solve them in parallel and across my new internet that was a new global network of 2 raised to power 16 or 65,536 coupled off-the-shelf processors. Those processors were equal distances apart and shared nothing but we are in dialogue with each other. I provided the complete details of my supercomputing inventions and did so across 1,000 podcasts and YouTube videos. I posted the most YouTube videos, YouTube lectures, because I have the most knowledge in the field of supercomputing. My YouTube lectures encapsulated the knowledge of mathematics, physics, and computing that I gained from nearly 50 years of fastest computing that began on June 20, 1974 at 1800 Southwest Campus Way, Corvallis, Oregon, USA. I had to be a polymath, not merely a mathematician, to work alone and solve the most difficult problem in supercomputing, which traversed half a dozen frontiers of scientific knowledge. In contrast, American scientists work in large teams. A person that was aided by 100 scientists might only understand 1% of the work and therefore cannot give an impromptu interview or deliver an on-the-spot lecture and do so without the support of PowerPoint photos. Having a supercomputer is one part of the equation for solving the most difficult problems arising in supercomputing. Only a polymath can translate and solve the toughest problems at the crossroads where new mathematics, new physics, and new computing intersect. The extra knowledge that gave me an edge over other mathematicians, physicists, and computer scientists was that I was the first person that could translate some laws of physics into a system of partial differential equations of calculus. The partial differential equation is the pillar on which the supercomputer rests. I converted those equations into their algebraic approximations. That is a system of partial difference equations of algebra. Finally, I invented algorithms and email primitives that are my final step-by-step instructions for my world's fastest computing. Each processor must execute in lockstep my programmed instructions and execute within and across millions of processors that shared nothing. Those were the mathematical conditions for inventing the world's fastest computing. I used my new supercomputing knowledge to solve the most difficult problems and solve them across the world's slowest processors. My contribution to supercomputing knowledge was in the news shortly after its discovery at 8:15 in the morning on July 4, 1989 in Los Alamos, New Mexico, USA. I invented the world's fastest computing, the way Bob Marley writes songs. The toughest problems in supercomputing traverses mathematics, physics, and computer science. For that reason, a supercomputing genius must be a polymath. The supercomputing polymath left his or her specialty for several years and left it to conduct research in mathematics or physics or computer science, and do so to gain a different perspective from each field. In my quest for how computing across processors powers the world's fastest computers, I left the frontier of knowledge of mathematics, known as partial differential equations and computational linear algebra, for the frontiers of knowledge of physics, known as fluid dynamics. I did so to become a mathematical physicist who investigated how to solve the most compute-intensive problems that arise during geophysical fluid flows. Supercomputing problems, such supercomputing problems include forecasting and hindcasting the global scale motions of fluids, that is, liquids and gases, that enshroud the Earth. Geophysical fluid motions include subsurface, multi-phased fluids flowing across anisotropic and heterogeneous porous media and flowing up to 7.7 miles or 12.4 kilometers below the surface of the Earth. Geophysical fluid dynamics, fluid motions, include centuries-long global climate modeling, executed to foresee otherwise unforeseeable global warming. After a decade following 1974, I left mathematical physics for the frontier of knowledge of the then unexplored field of the world's fastest computing across the world's slowest processors. Looking back and using a metaphor, I learned that if you've never left your house, it's impossible to have ever seen your entire house. In 1989, I commanded and controlled more supercomputing power than any person that ever walked on planet Earth. I understood the world's fastest computing deeper than the armchair theoretical physicist and deeper than the mathematician who never left his blackboard for the motherboard that occupies the footprint of a football field. I'm a polymath who sojourned from mathematics to physics to computer science and did so across half a century to leave behind a legacy of 1,000 podcasts and YouTube videos. Famous scientists who came of age after the mid-20th century were obliged to leave as their legacy a series of videotaped lectures. Each lecture must describe their contributions to mathematics or physics or computer science. Albert Einstein shared about 10 videos. I shared 1,000 videos in YouTube, each up to 4 hours long. My 1,000 podcasts and YouTube videos were the culminations of half a century of painstaking research that began on June 20, 1974 in Corvallis, Oregon, USA. Listening to only one of my podcasts instead of watching my 1,000 YouTube videos is by being misled by a single still frame photograph. It's like writing a book review after only reading one page of a 1,000-page book. My 1,000 YouTube videos permit their viewers to approximate my lecture experiences, but watch them without their visceral impact. As the first supercomputer scientist who came of age in the 1970s, it was imperative that I followed a different path to the frontier of human knowledge of the world's fastest computing across the world's slowest processors. At that supercomputing frontier, new partial differential equations of calculus and large-scale algebra intersected, and new algebra and fastest computing intersected. I visualized my world's fastest computing as occurring around a new internet that was a small copy of the internet. Both internets encircled a globe in the 16th and 3rd dimensions of hyperspace, respectively. My scientific discovery of the world's fastest computing occurred at 15 minutes after 8 o'clock in the morning of July 4, 1989 in Los Alamos, New Mexico, USA. That new knowledge was my breakthrough answer to a perennial big question that appeared in a science fiction story published on February 1, 1922. 67 years later, I was in the news as the African genius that won the highest award in supercomputing. Computer scientists call my award the Nobel Prize of Supercomputing. I won that top supercomputer award in 1989 because I discovered how to turn that science fiction story of 1922 to a reality that's a new spherical Ireland of 64 binary thousand off-the-shelf processors that could be harnessed and used to solve the most difficult problems in science, engineering, and medicine. The poster boy of the 20 most difficult problems is computing at the world's fastest speeds and doing so while executing large-scale, high-resolution global climate models and executing them to foresee long-term global warming and to find answers to previously unanswerable questions and create new branches of human knowledge such as the world's fastest computing across the world's slowest processors. The indication of my contributions to the development of the fastest computer is not merely that I recorded the fastest computer speed, but that I did so via my new paradigm of communicating and computing across an ensemble of millions of processors, rather than via the old paradigm of serial supercomputing or vector supercomputing within one fast processor. I was in the news in 1989 because my recording of the world's fastest computer speed that I measured across the slowest processors in the world was a technological feat considered impossible at that time. My discovery of an alternative way of recording the fastest speeds in computing inspired the change in the way we look at both the computer and the supercomputer, and inspired the radical departure from vector computers that solved one problem at a time and was the size of a refrigerator to the first supercomputer as it's known today that solves millions of problems at once and that occupies the space of a soccer field. And it costs the budget of a small nation, or $1,250,000,000. Because the fastest computers in the world are precious. Each is protected by armed guards and is classified as a state secret. For economic and national security reasons, the US barred China from buying American processors and using them to power Chinese supercomputers. China understands that dominating the $45 billion a year supercomputer market is its stepping stone to dominating the globe in scientific discoveries and technical breakthroughs that are the preconditions to becoming the world's superpower. In the 1970s and 80s, my scientific search was for answers to the most important questions at the crossroad where new mathematics, new physics, and the world's fastest computing intersect. My quest demanded that I look beyond the frontiers of mathematics, physics, and computer science. I did so because I realized that the discretization of the partial differential equations of calculus is an inadequate answer to the big question of how do mathematicians solve the initial boundary value problems of mathematical physics. Such problems govern the high-resolution global climate model that must be used to foresee otherwise unforeseeable long-term global warming. Mathematical knowledge alone was an inadequate answer to big questions just as the technological knowledge of the fastest computing across the slowest processors is also an inadequate answer to the science fiction question of how to design, manufacture, and program the ultimate supercomputer of forthcoming centuries. Looking back to 1974 and 15 years onward, those that insisted that I remain in only one field, such as mathematics or physics or computer science, were standing in the way of my invention of the first supercomputing across the world's slowest processors. Fastest computing was not entirely within mathematics or physics or computer science. I discovered it at their intersection, and did so when the naysayers were standing in the way of the critical and enabling parallel processing technology that now underpins the world's fastest computer, and that would allow faster computers to emerge from an ensemble of millions of slower processors. Being at the frontiers of knowledge of the fields of physics, calculus, algebra, computer, and internet sciences is the minimum requirement to becoming the first person to solve the most compute-intensive problems central to supercomputing. Abstract mathematical physics is the most recurring decimal inside the billions of processors that define and power the world's fastest computers. Therefore, if I didn't understand the computational physics, or the abstract calculus, or the large-scale algebra, which I was inventing on my blackboard, and which I was supercomputing on and across my 64 binary thousand processors, then my chances of discovering how to parallel process and do so to compute at the fastest recorded speeds demanded that I achieve a one problem to one processor correspondence for my 65,536 initial boundary value problems of extreme scale computational physics. That one-to-one correspondence was the mathematical precondition to solving the parallelized problems at once. Without that one-to-one correspondence, my chances of recording the fastest computer speeds were as good as having 65,536 monkeys typing on as many computer keyboards, and then expecting their asynchronous typing to record a 64 binary thousand-fold increase in never-before recorded email and supercomputer speeds. In retrospect, the reason I was the lone programmer of the most massively parallel supercomputers of the 1980s was that I was the only person that could execute fastest computing across billions of processors and solve the once impossible to solve grand challenge problem of supercomputing. I solved that grand challenge problem because my confidence came from knowing who I was, what I was doing, and who I am. My first night in the USA was spent alone in 36 Butler Hall, Monmouth, Oregon, and on Sunday, March 24, 1974. I was then 19 years old. I was the supercomputer scientist in training that emigrated from Onitsha, Nigeria, a commercial city in the heart of sub-Saharan Africa. I came alone to Oregon in the heartland of the Pacific Northwest region of the USA. I came and became the mathematician that discovered new mathematical knowledge. Over the following decade and a half, I grew and evolved and found myself beyond the farthest frontier of high-performance computational mathematics, Computing across millions of processors was the jagged, multidisciplinary frontier of supercomputer knowledge. For the 16 years between my supercomputer research in Corvallis, Oregon, and Los Alamos, New Mexico, I felt like an explorer that walked alone with a dim lamp and along a small road that was the holy grail of the world's fastest computing. During my 16-year-long quest for how to harness a million processors and use them to power the world's fastest computers, I learned to distinguish between experiment and theory, between theory and discovery, and between fact and fiction. And I learned to know for the first time that a theory is an idea that is not positively true. In the decade that preceded 1989, I invented supercomputer algorithms grounded on mathematical equations from the laws of physics. Specifically, I invented partial difference approximations of large-scale computational linear algebra that approximated partial differential equations of calculus that encoded the second law of motion of physics that was discovered 3 centuries earlier. I invented equations of mathematics grounded on the laws of physics, and I heard and trusted my inner voices that were almost drowned in a cacophony of secondary voices. Thank you very much. I'm Philip Emeagwali. Thank you. Thank you.
Insightful and brilliant
Thank you
lecture.
very much.